Okay, today we're going to talk about renewable integration challenges. So, the quasi final exam questions for today are what are the primary challenges associated with increased dependence on variable renewable energy like wind and solar? Number two, how do these issues impact other power plants, conventional generators, and larger power system operations? And then, what are the financial and economic issues that variable renewable energy can cause um, in wholesale electricity markets? So, a lot of the issues related to variable renewable energy come down to a couple things. The first is that they're non-dispatchable, which means they can't be scheduled. We also experience multi-scale intermittency. So variable renewable energy comes and goes on multiple time scales, and then there are also geographical limitations. So let's take these one by one. First, talking about the non-dispatchable nature of wind and solar. So we can turn these resources off. We can curtail them somewhat at will, but we really don't have much of an ability at this point to turn them on or increase or decrease production at will. So, why is this a problem? Why is it important to have some types of power plants that we can turn on and can ramp up at will? And so, the answer to that is that we have electricity demand that fluctuates all the time. And traditionally, we've relied on a diverse portfolio of different generation resources, each of which has different capabilities, different costs, but also engineering characteristics that allow us to either turn them on and off quickly or to turn them on and leave them on for extended periods of time. So we need historically some types of resources that we might refer to as peaking or ramping resources to be able to turn them on and off and also ramp them up and down in order to meet that fluctuating electricity demand that we collectively have. The other issue is multi-scale intermittency. So when we talk about wind and solar varying, they can vary on different time scales. They can vary throughout the day, obviously, throughout the week, seasonally within a year, and also year to year. And sometimes these changes in resource availability can be unpredictable, which makes them even harder to deal with. So this figure shows seasonal and interannual variability in different types of renewable energy. And I'll just sort of call your attention to wind and solar in particular. So wind here is shown in gold, and solar PV is shown in light green. And what you can see here is a pretty clear seasonality. And this is for total aggregated capacity factors over the entire United States. So for wind, we see that if you sort of added up all the wind power in the United States, the lower productive periods of the year would be late summer. The higher periods of the year would be winter and spring and fall. And then for solar, the higher periods of the year are during the early summer, late spring, and the lower periods are during the winter. We also see some year-to-year variation. So we have about 3 years of data shown here. And in particular, you can look at solar. Year three, that peak, that typical summertime peak that we might expect, doesn't seem to materialize, whether that's because of increased cloud effects or really hot temperatures that reduce the efficiency of panels. It's hard to say. But what's clear here is that on a year-to-year basis, the amount of electricity that we're getting from these sources can vary. This figure shows seasonality in renewable energy production, particularly for wind power. And that seasonality here depends on where you live, right? So if you live on the West Coast in the Northwest or California, the peak periods of the year for wind power production tend to be in the late spring, summer. And that's the exact opposite of the rest of the United States, where that period of the year tends to be have lower productivity in terms of wind power production, with the highest available production happening in the winter months. We also see that seasonality for solar depends on where you live. That's particularly true when we look at the influence of latitude, which changes the rate of solar insolation and the seasonality of solar insolation throughout the year. So if we live right at the equator, we experience about the same amount of solar insolation throughout the year. That's what this blue line shows. But if we live really far away from the equator, either north or south, we have certain periods of the year we have lots of solar insolation and it doesn't get dark. That would be the gold line. And then other periods of the year where we don't get any and it's completely dark during the day, especially during the fall and winter. And then we have those red and green lines, which represent latitudes that are in between 0 and 90 degrees. So latitude also influences or is a primary influence on the rate of solar insolation and the availability of solar power. We also can look at resource availability and fluctuations in wind and solar power production on shorter time scales, so subseasonal, both hourly, daily, and weekly fluctuations. And so this is a representative time series of offshore wind power production over 2 weeks off the eastern coast of the United States. And what we see here is 336, I think, hours, which would be 2 weeks. And you see a high degree of variability, but you also see periods of sort of sustained low wind power production and sustained high wind power production, with a lot of periods in between where wind is going up and down. So you have what you could think of as whole days that aren't windy and whole days that are, and then some days where it's windy some part of the day and not windy others. And this is 4 weeks of solar PV production. I'm not sure exactly from where. And so we see less variability in terms of the within day pattern. And that's because of the greater consistency in terms of solar insolation received on an hourly basis. But we do see on a day-to-day basis a lot of variability in terms of how much solar insolation is incoming in this area, and that impacts on a day-to-day basis how high those peaks go, so how much solar is actually produced by panels. And we also might experience more rare events like solar eclipses in the case of solar power production that we would certainly be able to predict, but might have a very significant influence on the total amount of power we could expect from installed solar. And so this illustrates the expected decrease in the amount of solar power production in Germany for the solar eclipse that occurred in 2015. So in addition to variability, uncertainty is a big issue. If we were just relying on wind and solar that were both variable resources, but we could predict exactly how they could vary, that would be significantly easier to manage because a day in advance we would know if we were going to have wind power production or not, and we could plan accordingly. But part of the challenge in integrating renewable energy, variable renewable energy, is that those fluctuations we can't always predict. There's uncertainty on a daily basis, on a seasonal basis, in how much is going to be there. And we might be able to describe probabilistically what the chances are that we have a certain amount of wind power production. But ultimately, it's not something that we are always able to predict. Sometimes there's error involved. And so it's a little bit like rolling a dice. And so that's what this figure shows. This is a probabilistic representation of offshore wind power production over a 25-year period. And so the black represents the 50th percentile. And if you think about the bell curve, assuming this was a normal distribution, that black line might represent the mean. And then the colors, the different shades of blue represent the different probability ranges. So the darkest blue represents the interquartile range. So the 25th to 75th percentile of wind power production. So the values closest to essentially the mean are shown in dark blue. And then the lighter shades of blue represent the 10th to 90th percentile, and then also the minimum and maximum wind power experience. So you can see for any given calendar day of the year, there's a very wide range of possible values that it could take. Most of the time, those values are clustered around that black line. But for any given calendar day, you could experience either a very, very high value or a very, very low value, although in both cases, experiencing those extremes would be not very likely. We can also look at uncertainty in variable renewable energy production on larger time scales, right? On a seasonal or year-to-year time scale. And a great example of that is actually this wind drought that occurred in the Western United States that occurred several years ago, around 2015. And what this figure shows, you have three different figures or pictures of the United States that represent a couple different months at a time: January to March, April to June, and July to September. And the colors represent deviations from the historical average or anomalies, right? So the warm colors represent higher wind speeds than average in terms of percentage. And the colder colors, so blue and purple, represent less wind speed, lower wind speeds than average. And what you can see from January to March and April to June is that much of the United States experienced significantly lower wind speeds than average for a prolonged period of time, many months. We can also think out ahead many years into the future and wonder how climate change, right? The problem that we are trying to address using variable renewable energy may itself impact resource availability in terms of wind and solar. And so what this shows are projected long-term changes in wind power due to lower wind speeds or changes in wind speeds by the year 2100. And so the light blue represent changes in actual kilowatt hour outputs, and the dark blue represent percentage changes. And you can see that in particular in the central United States, which is the best area in the United States to install wind power capacity based on wind speeds alone, climate change is actually projected to significantly reduce wind power output from those turbines. So one of the other really important challenges that relying on variable wind and solar raise, it has to do with geographical limitations. So we've talked about this a little bit before, and this has to do with the fact that wind and solar resource availability is not uniform across space. And it may not be greatest where people, which is the demand for electricity, are actually located. And so we've seen this figure before. This shows, this is a map of average wind speeds across the United States, including offshore areas. So in terms of land-based wind resources, clearly the highest potential exists in the central part of the United States, the Great Plains and Texas and Oklahoma. Unfortunately, that's an area of the United States where population is least densely concentrated. And what that means is that installing a lot of wind turbines in this area and expecting it to get to places where people would actually be consuming that electricity would require a significant increase in transmission capacity to get that wind power from the point where it's produced to the point where it could be consumed. Solar power potential also exhibits geospatial gradients. And what this shows is that the areas of the country that have the highest potential for electricity production from solar PV are the southwestern United States. And you can see that other areas, including the northwestern United States and the northeastern United States and Alaska, have pretty low resource potential in terms of solar. Now, that doesn't mean that we're not installing solar in those places. We talked about in the lecture on solar power that because retail electricity prices are high in some of those places, especially the Northeast, residential or rooftop solar is actually a pretty attractive option. Even though the panels themselves don't produce that much electricity, it is a way for those customers in those regions to save money because their retail electricity prices are quite high. So geographical limitations can also unfold on shorter seasonal, daily, or hourly timescales. What that means is that wind and solar might be temporarily plentiful in one place and scarce in another before switching back and forth. So we can think about that variation in resource potential across space happening on a seasonal basis, and we've already sort of alluded to this with an earlier example. So this is monthly median wind plant capacity factors over the United States. So the way you might think about this is that while the west coast of the United States is experiencing lower wind power production during the winter months, the rest of the United States is experiencing higher wind power production. And then during the summer, that flips, where the west coast experiences higher wind power production and the rest of the United States experience lower. So in theory, I guess you could be producing a lot more wind on the west coast during the summer and sending some of that extra into the other parts of the United States, and then have that flow of electricity switch during the other parts of the year. We also see similar issues like this on higher time scales, on a daily or hourly basis. And so what this map shows, the colors actually represent different electricity prices. So one of the things that we haven't really talked about and won't in great detail in this class is the fact that electricity prices can vary in a network spatially. And so this is called locational marginal pricing. And the reason why electricity prices can vary like this spatially is due to transmission constraints. And so what the warm colors represent are high electricity prices, and what the cold colors represent, especially the dark blue and purple, are very low electricity prices. In fact, what we see here is that the area of this map labeled with the A is actually experiencing negative electricity prices, which we'll talk about in just a minute. And so what that means is that that area has way too much renewable energy, presumably wind. And it would like to get some of that electricity out of the area labeled A and over to that area labeled B that could use some of that low-priced extra wind power. But the reason you have this gradient, where you have this sort of concentric circled area of high prices in B and low prices in A, is because of transmission constraints. This barrier clearly indicates that there is not a way to get that extra electricity out from the area labeled A over to the area labeled B. So all of this is to say that the bottom line is, if we want a future grid that is dominated by zero carbon energy, it can't just be wind and solar. Those resources by themselves are not sufficient to provide reliable electricity in modern AC power systems. So then the question is, what else would we need in addition to wind and solar to make sure we get a grid that is dominated by zero carbon, but also one that is reliable?